Okay, so going back, this is again material from lecture number 10, I believe, which is the transportation model and the assignment model. So this was the example we discussed in class, and I was basically telling you that the transportation problem follows the same format, even though you can have different information, different type of problem. If you identify that the problem can be modeled as a transportation model, you would expect to have this typical type of objective function, which you're trying to minimize the cost of moving items from one point to another. And also you will have a group of constraints that look at the supply and a group of constraints that look at the demand. Okay, so that's the three main characteristics of the transportation problem. So in this case, we were trying to move some items from these three cities, Los Angeles, Detroit, and New Orleans, to these two cities, Denver and Miami. And we know the cost to move from each city to each destination, and we know the amount that you can supply and the amount that it is expected in your demand. So the problem is clear, right? Everybody knows what we are trying to find out. So we're trying to decide, using our decision variables, how many units should we send from Los Angeles to Denver and how many from Los Angeles to Miami, and so on. So the decisions are going to be affected by the cost. In this problem in particular, something that was assumed is that the demand and the supply is the same. So you're going to supply, you're going to have enough items to supply the demand. So for that particular case, and I already post this spreadsheet in your track site. So essentially what you needed to do was to put the information I provided from the problem, so you know the cost to go from one city to the other, right? Maybe I can increase the size of the here a little bit. And you also know the supply, Los Angeles, Detroit, and New Orleans is supplying this amount, and demand for those two cities. Okay, so you need also to basically define where your decision variables are going to be. You know you have x1, 1, x2, 1, and so on. So here I'm identifying my I indices, which is your supply node, and my j indices for your destination. So x11 is this cell, x21 is this cell, and so on. Okay, so we have 6 decision variables, which were the same ones that were in the slide. And then, you know that you have 5 constraints, so you need to define those constraints using the information that you already have in your spreadsheet. So for instance, if you go to the first constraint, let me show you here. So your first constraint is x11 plus x12 equals 1,000, right? So if you go to your spreadsheet, this is what you have. D11 plus E11, which is x11 plus x12. And that is in this cell. Same thing for the next constraint. You will have this cell plus this cell, which are your variables, will be equal to 1,500. And this cell plus this cell should be here equals 1,200. So I can show you this here. You see, that's your second constraint. I apologize. This just okay. So the last two constraints are the ones that look at the demand. So you have x11, x21, and x31. How would you code that constraint in Excel? What would you do? And that is this constraint right here. So if you were to formulate, or if you were to code this constraint, the one that I just showed you, what would you do? And it has to go here. It will be this cell. Correct. So you're going to sum these three cells, and that will be equal to the demand of Denver. And then this, we'll look at Miami. So it's this one, this one, and this one equals 1400. Okay, so once you have the model, the formulation, you put the data that is provided by the problem in the format that you can understand. The most difficult part will be here, this square right here, which is the one that defines the variables in yellow. You need to place or locate where your decision variables are going to be, and also you need, using the information and the decision variables, you need to code the constraint. So those are the main two things, or the most difficult part when you're trying to code the spreadsheet to solve the problem using Excel. So once you have the constraints and decision variables, then what you can do is just go here to data, solver. This is already done, so you know how to fill this table. Solve, solution, okay. So the solution is the following, is the one that was already there. So you're going to move 1,000 units from Los Angeles to Denver, and you're going to move 1,300 units from Detroit to Denver, and also from Detroit to Miami you're going to move 200, and from New Orleans to Miami you're going to move 1,200. So that's the solution. And that will give you a total cost of, here, you're trying to minimize your cost, this is going to be your total cost. Okay? Any questions? It's important that you understand this because I'm asking you to do the same thing in your homework. So you're going to have to solve these problems in your homework. There's two problems that you're going to have to solve using the solver. Yes?
The yellow one, the answers were there in yellow?
Yes.
So we're just putting in the, okay.
So initially, when you So what you do initially is, this is the way that your model is going to look without the solution. You know that your solution is going to be there because when you code your solver, you are telling them where your changing variables are. So you come here and you select those spaces because you know those are your decision variables. Your objective function is here. And again, let me go reinstate this. So when you code your objective function, you are basically doing the same thing that you do for your constraints. So you need to use the information you have from the table or from the information provided by the problem and code the formula for the objective function. So in this case, you know that the cost is the cost times the decision variable. So it's this cost times this, D5 times D11, plus this cost times this cell, D5 times D12, and so on. Okay, so here's your decision variable. At the beginning, they're going to be empty because your solution is going to be placed here once you solve the problem. So you know the objective function. So you set the objective, you want the objective function, you go to the cell, then you want to minimize this problem, so minimization, changing cells, those are your decision variables, and here the constraints, you're basically selecting these constraints that you already stated. So when you solve the problem, you go here. Again, you need to solve using the simplex because this is a linear program. And we are also making them positive by checking this part here. So we know that all our decisions at least should be 0 or positive. So when you solve, there was something. Then you will see the solution here. So these are your changing cells. These are your decisions. So you know now the optimal is sending 1,000 from Los Angeles to Denver. Now, you can play with this. So for instance, right now you're sending 1,300 from Detroit to Denver, right? What will happen if I put here 3,000? You can solve this problem again. Any idea what will happen? You're increasing the cost from that city, from Detroit to Denver. So you will probably see a reduction in terms of the number of units that you're going to be sending from Detroit to Denver because it's going to cost you more. If you don't have any other alternative, then that will remain the same. But let's find out. So there you go. Since you increase the cost, now instead of sending those units from Detroit, you're sending more units from your units. Because it's costing you a lot of money to send them from here to here. So that's the type of analysis that you can do. If you increase the cost, this is what's going to happen. If you decrease the cost, this is what's going to happen. And I did that just by changing numbers. Once you have your solver ready, it's just a matter of the type of analysis that you want to perform. So let me go back to previous solution. So in the previous solution, this was 100. So if you solve this again, you'll go back to the same or the original solution. Now there was a case on that same lecture, and I'm going to make this video available, so if you want to go back and review what we're doing in the spreadsheet and everything, you can do that. There was another case here. Okay, right here. So here we were looking at the problem where you don't have a balanced demand, meaning that you have less supply than the demand that you're seeing. Okay, so in such a case, we said that we were not going to be able to find a solution. And the problem here is telling you that what if the capacity in the Detroit plant is 1,300 instead of 1,500. So what I told you is going to happen is you will not be able to find a solution for this problem. And let's see that in the computer. So on the same file, I have another model here. The second worksheet is looking at that particular problem. So if you look here, I'm changing that demand from 1,500 to 1,300. So now the demand is less, and if you add this, this is 3,500, and this still 3,700. So when you try to solve this problem, the model or Excel is going to tell you solver could not find a feasible solution because there's no way that you can satisfy those constraints. Since your demand is less, your supply is less than the demand. Okay, so what was the solution for that problem? Do you remember what alternative or what modeling trick we can do in order to find a feasible solution? Correct.
Right?
Sure.
So you set up the dummy plan, and you get like a number that the dummy plan is that number just represents how short.
Yes. It doesn't mean that you're going to be satisfying the demand. It just means that the plant that is going to be sacrificed or the one that is not going to be receiving the number of units is that particular city because it's going to cost you less than keeping the other ones with the full demand. So if you go here to the third model, here is where I add that dummy plant. So as we explained in class, we are adding that dummy plant and we are putting zero cost. Okay, so there's no cost because this plant does not exist. We are also adding that in our decision variable. So we're going to have some decisions for the dummy plant as well. And we also need to modify our constraints. Okay? Because we need another constraint for our supply. Our supply. Okay? So if you solve the problem now, you're going to find a solution. Solver found a solution. And this is what the solution we saw in class. So now we are sending this many units to each city, but we know that this number here is saying that we are not going to be able to satisfy the demand for Miami by 200 units because this plant does not exist. This is just a modeling trick to solve the problem. Now, this can be seen in a different way. For example, let me see if I did that here. So I need to add one more thing here, plus this times this plus this times this. Okay, so that's our cost right now. It's almost 300,000. Now, we are saying that the dummy plant has zero cost. There's no cost because this plant does not exist. But we can see this from a different perspective. If we don't want Miami to fall short with their demand, we can put a cost in that particular city or that link that will represent the cost or a penalty cost. Meaning that if you don't satisfy that demand, you're going to incur in a cost. If I want to force the model to satisfy the demand for Miami, I can put a high cost here. So the model will try to satisfy that demand and not incurring that particular cost. So this is what I'm saying. I know right now I'm able to satisfy the demand for Denver, but not for Miami. But Miami is more important. It's a more important client for me. So I need to satisfy that demand. So I will put here a cost. Let's say the highest cost that we have here in the table is $215. So I'll put a cost that is higher than that one. I'll put 300. Now, if I solve the problem now, you should see that the solution will satisfy the demand for Miami, and Denver will fall short. So let me solve this. Solve. Here you go. Now it's less expensive for you to leave Denver with the shortening in their demand than having Miami with the short demand. And that's just done by adding that cost. Is that clear? Initially, there were not costs, so any of the two cities can independently, you can leave one of the two without the complete demand. But now you have a cost. Let's say if you don't satisfy the demand for Miami, this client is not going to buy it for you anymore. So you know it's very important to satisfy the demand for that client. So you can put a cost here, a high cost. You don't want to lose that client. You put a high cost there, you satisfy the demand for that client, you fall short for the other one. Any questions? Okay, so again, this is going to be available on Tracks. I'm also going to post a video. Let me know if you have questions. Okay, so that basically concludes the lecture on the transportation problem. And now we can go back to our discussion for integer programming. And today, you'll see that we're going to finish the examples. Again, these examples are typical problems that can be solved using integer programming. But we're going also to discuss how to solve these problems using one of the methods for integer programming, which is called the branch and bound method. So, we discussed the capital budgeting allocation problem, and here you were basically trying to find out what was the best way to invest using a limited budget. So you needed to decide based on the net present value which project was the best for you. And we formulated that problem, and we conclude that this problem is typical, and you can find a lot of applications in which you can use this format. This is called the knapsack problem because you only have one objective function and one constraint. This constraint is called the knapsack constraint because you are basically adding items to your constraint until you reach this capacity. It's like putting stuff in your bag. You're still adding stuff there until you reach the capacity. That's what this problem is doing. And you want to maximize your profit or your revenue based on the number of items that you can accommodate in that bag. That's an abstract problem. Can I go to the next slide? Okay. So we discussed this. Then we also talk about this problem The main thing about this problem was that you had a rental cost to take into account, and you will only rent a particular machine only if you needed to produce a particular product. So if you produce a shirt, then you needed to rent that machine to produce shirts. But if you were not going to produce those shirts, then you didn't need to buy or rent that particular machine. So we talk about this. Here's the decision variables, formulation of the problem, then show you this solution, and there was y1, y2, y3 equals 0. That means that you're not renting any of the machines, so the solution is incorrect. So you needed to add this constraint to the problem in such a way that you can find the optimal solution. But there's still an error here, and nobody catch the error. Anyone can see the error? Anybody? A point? A point for the second exam? It's in the solution. It's not in the formulation.
We didn't write out all
No. What does this say? You're going to produce what? X3?
wait, fine.
X3, number of pants that you're going to produce each week, right? So you're saying that you're going to produce pants, but you're going to rent a machine for the shirts. So if you're going to produce pants, you need to rent this, and it's a typo. And I did it on purpose just to check if you were following. So this should be Y8. So if you are solving this problem in Excel, the solution will basically give you the right solution.
Yeah, but put the constraints the X one.
Yes, yes. You need to put those constraints in order to get the value for your y's. If not, you'll see that the y values will be 0. This is the link between the x and the y's. So in order to link those two variables, you need these constraints. So this should be y3. Okay. So let's go to the next problem. What is the problem with these characteristics? Called a fixed charge problem. In a fixed charge problem, there is a cost associated with performing an activity at non-zero level that does not depend on the level of the activity. For example, the renting of the machine. Practical applications, facility location problems, and production planning problems. So those are the type of applications in which you can find this type of formula. Okay, so this problem is also very well studied and also very important, especially for government agencies in charge of building government offices, fire stations, and hospitals, schools, and so on. So basically, the set covering problem in this particular example, there are six cities in this county. The county must decide where to build the fire station. So here we have three pieces of information, two different tables. The first one is the time required to travel between cities. So if you go from city 1 to city 1, you know that you're already there. But if you go from city 1 to city 2, this is the time that it's going to take you to get to the second city and from city 1, and so on. So if you go from 1 to 6, it's going to take you 20 minutes. To go from 4 to 1 takes you 30 minutes. From 4 to 35, from 4 to 2 takes you 35 minutes, and so on. So this is the time that will take you to travel from one city to another. Now, the cities within the 15 minutes of a given city, so you can use this information to basically map which cities are within the 15-minute radio of each city. So if you go here, city number 1, you know city 2 and city 1 are within 15 minutes. If you go to city 2, you have city 1 and city 6 and city 2. So this is what this table is doing. City 3, of course, city 3 and also city 4, which is here, 3 and 4, and so on. So the county wants to build the minimum number of fire stations needed to ensure that at least one fire station is within the 15 minutes of each city. So this should be fire station. Okay, so we have to make a decision when are we going to place this fire station. The only constraint we have is that we want to place it within the 15 minutes of each city. So how many fire stations should be built and where they should be located? That's the question. So our formulation, our decision variables, if you want to place a fire station in city I, then that will be equal to 1. If not, then that decision variable will be equal to 2. So again, we have 6 cities, so we're going to have 6 decision variables. The objective function, you want to minimize the number of fire stations to build or to be built. So the maximum number of fire stations are 6. The minimum, you don't know. That's why you want to find out. So constraints. So in these constraints, we are using the information from here. So we know that to cover city 1, you have to place one fire station in one of these 2 cities, because those are the 2 cities that can reach this city 1 in less than 15 minutes. Same for city number 2. If you want to reach number 2 in less than 15 minutes, then you need to place a fire station in one of these 3 cities. If you want to reach 3 in one of these 2 cities, and so on. So this is the information that you're going to use to build your constraints. You want to cover all the cities. You know the cities that can arrive in less than 15 minutes from one point to the other for each city. And you want to make at least one fire station to reach one of these cities. So if you go here, X1 and X2 are the ones that can reach city number 1. X1, X2, and X6 can reach city 2. X3 and X4 can reach city number 3. X3, 4, and 5 reach city 4. 4, 5, and 6, city 5. 2, 5, and 6, city number 6. And you want to make that greater or equal to 1. Because you want to have at least one station. Okay? And the constraints, the objective function will basically force a problem to have the minimum number of stations. So you know if x2 equals 1, then you will cover city 1, 2, and 6. Right? Because it's part of this constraint, and this constraint. X4 will cover the remainder, so that can be an optimal solution. Just by looking at the problem, you can see. So here you have these two, and this one, and then these. So having x2 and x4 equal to 1 will satisfy all the constraints and will cover all the cities. And it will be the minimum number of stations because there's no city that can reach them all. So the minimum will be 2. Does that make sense? Okay, so if you have x4 equals 1, this is going to be greater or equal to 1, this is going to be greater or equal to 1, and this one is going to be greater or equal to 1. If you have x2 equals 1, these 3 constraints are going to be satisfied. So the optimal solution for this problem is x2 equals x4, which equals 1. Questions? Okay. So I think this is the last example. We are given, in a set covering problem, we are given a set of objects, and we are also given a set of subsets. Each subset even has a cost associated with it, and the problem is to cover all the members of this main subset at the minimum cost using the member of the subset. So again, the main subset are all the cities. The subset is just those cities that can be reached within a 15-minute length. So the properties, the problem is a minimization, and all constraints are greater or equal. All right-hand side coefficients are 1, and all other matrix coefficients are 0 or 1. So 3 problems, 3 main problems. Those are the examples: the knapsack, the set covering, and the fixed chart problem. Okay. So now we know the difference between linear programs and integer programs. What's the main difference? Anyone knows? Linear programs, integer programs, what is the difference? Right. So your decision variables are integers. So in linear program or linear programming, decision variables are greater or equal to 0, but they can also take fractional values. In integer programming, decision variables are also greater or equal to 0, but they are integer. So you're forcing your decision variables to have integer solutions. That's the main difference, and that creates some problems in terms of finding the solutions. As I explained early or in our previous lecture, when you look at the feasible region of the linear program, you can have something like this. But the integer programming solution is going to look at those points where you only have integer values. So your feasible region is now smaller. So in order to find, you know that we can find the optimal solution for a linear program using the simplex method, in which you move from point to all the corners, from this point to this point, from this point to this point, from this point to this point, and you're guaranteed to find an optimal solution. But here you don't have that flexibility anymore. If you want to find a solution, you need to search on those points that are integers. And that makes the problem difficult to solve, very difficult to solve. So now we're going to focus on one of the solution methods for integer programming. So again, integer variables make an optimization problem difficult to solve. Memory and solution time may rise exponentially as you add more integer variables. Even with highly sophisticated algorithms and modern supercomputers, there are models of just a few hundred integer variables that have never been solved to optimality. Anyone knows about the traveling salesman problem, in which you have to move from one city to another. You want to find the best solution for this person who is traveling from one point to the other. That's a very hard problem to solve. And that's one of the problems that when you increase the size of the problem, when you have more cities, you can get to a point in which you cannot find an optimal solution. And that's why people have been, it's a very important problem, very useful in the industry. And that's why there's a lot of people looking for ways to find solutions for that type of problems. And there's some methods that give you good solutions, but none of them are optimal, like best of all. So this is one thing that you need to understand when you have integer variables, when you have these very complicated problems, you might find out that there's no way that you can find a solution. This is because many combinations of specific integer values for the variables must be tested, and each combination requires a solution of a linear or nonlinear optimization problem. The number of combinations can rise exponentially with the size of the problem. And in this class, we're going to look at the very simple case in which we only have two variables, and we're going to see how the process works for finding solutions for an integer program. Can I go to the next? So the method we're going to look at is called the branch and bound method. It will yield the optimal solution. It is more efficient than enumeration. So you can always solve the problem by enumerating out all the options. And you'll get to a point in which you are comparing when you compare all of the options, you should be able to find the optimal. But that process of enumerating all the options will give you hard time, and also you're going to spend a lot of time trying to find the optimal. So enumeration is an option, but it's not the most efficient option. It's very time consuming. So there's a couple of people who have come with these strategies. One of them is called the branch and bound method. So usually IPs are solved by some version of the branch and bound procedure. In the branch and bound method, implicitly enumerates all the possible solutions to an IP. By solving a single problem, many possible solutions may be eliminated from consideration. So you follow the strategy of the enumeration, but at some point, this method will tell you, okay, let's start branching from this solution. If you get this number, do not look more in that particular branch, follow the next branch. And you'll see how that works. So let's look at this example. It's called the Telfar Corporation, manufacturers tables and chairs. So you have the conditions for manufacturing tables. You have the number of labor hours for tables and chairs. Is also both have that 1 hour labor requirement. You have some requirements in terms of the materials. So this is the square board of feet of wood, and here you have the profit that you're going to make. So more material will give you more profit. Less material will give you less profit. Currently, 6 hours of labors and 45 square board feet are available. Formulate and solve the IP to maximize the profit. So what we are trying to decide here, we want to maximize our profit. We want to decide how many units of each we need to produce. So a number of tables manufactured and number of chairs manufactured are all decision variables. The objective function is to maximize the profit, and we have some constraints. One for the labor. Labor hours are 6 hours. So we have 6 hours of labor, and we have 45 square board feet of materials. So that's our second constraint. And of course, our decision variables will now be integers, because you cannot produce half a chair, you cannot produce 1.5 table. Okay, so you want the solution to be integers. You want to see 10 and 2 or 5 and 5 and so on. So we have our formulation here. So now I'm going to go through the steps for the bench and bound method. And I think all of you have all these notes. So if you can look at the screen, try to follow what I'm going to be doing. I think that will help you more. So the first step is to solve the LP relaxation of the IP. Remember what does that mean? Solving the LP relaxation. I said it in the previous lecture, but in case you don't remember, you can always solve the IP model relaxing these constraints. So you can solve it using the LP method, and at the end you will get fractional values. Those are numbers that you cannot use, but you can get a first solution. And that initial solution is what we are looking for. So if you solve the LP relaxation of the IP, this is first constraint. This is the constraint for the labor, for the material, and this one is for the labor. So what we are doing is we are solving the problem using the graphical method. So here we have our feasible region, and the optimal solution to the LP problem is this point. Right here. So the optimal solution to the LP relaxation is x1 equals 15 over 4 and x2 equals 9 over 4. Again, these are fractional values, and we are looking for integer solution. So we got our LP relaxation solution, and we know, based on the figure that I show you, that the optimal value of the LP, of the IP, or the integer program will be always less or equal to the LP relaxation. And that is because the feasible region of the LP is always bigger than the feasible region for the integer program. It's not working. So you can see that from here too, but show you here. So if you find that the LP solution is this point, you know that the feasible region of the integer program is going to be smaller, so you're expected to find the optimal solution for the IP here, which means that it will be less than or equal to the LP solution, always. If you find that the solution of the IP is greater, then there's something wrong. Okay? So here, this implies that the optimal value for the IP cannot exceed this number. So the optimal value for the LP relaxation is an upper bound for the problem. Okay, so we start. This is something that you already know. You know how to find the optimal solution using the graphical method. We found the optimal solution, but we know this is not an integer solution. It's a fractional value, and we are interested in the integer solution. So step number 2, partition the physical region for the LP relaxation in an attempt to find out more about the location of the IP's optimal solution. Okay, so you're going to choose arbitrarily a variable that is fractional in the optimal solution to the LP relaxation. So I'm going to choose x1. This is the variable. And again, this is coming from your solution. So x1 equals 15 over 4. I'm choosing that one. Yeah, it could be in either one. Okay? So you choose that one. Observe that every point in the physical region for the IP must be either x1 less than or equal to 3 or x1 greater or equal to 4, because we are looking for an integer solution. So if x1 is 3 point something, then the integer solution will be to the left or to the right of that fractional value. So if this solution is 3.6, you know that the integer solution will be or here or here. So that's why it's very important to get an initial solution. Okay. So with this in mind, we can branch on the variable x1 and create the following subproblems. We're going to call them subproblem 2 and subproblem 3. So subproblem 1 is this one, in which you have all the feasible region. We're going to add these constraints, x1 greater or equal to 4, so that will have this area covered, and x3 greater or less than or equal to 3. And that's what we're doing in our graphical solution. So we are adding those two constraints here and here, and now we are splitting this feasible region in two areas, this area and this area. Okay? So now things are getting more, a little bit more complicated. So now we have two subproblems. Instead of the whole area, we have two, because we are adding those two constraints. Because subproblem 2 and 3 were created by adding the constraints involving x1, we said that the subproblems 2 and 3 were created by branching on x1. And this is where the name of the method comes from. It's called the branch and bound. You are branching, you are taking x1 and you are branching x1. Now you have the value x3, x1 equals 3, and x1 equals 4. So step 3, choose any subproblem that has not yet been solved as an LP. We're going to choose any of the two. This is subproblem 3, and this is subproblem number 2. You can see the names here, subproblem 2 and subproblem 3. So we're going to choose subproblem number 2, and we're going to find the optimal solution for subproblem number 2, which is only in this area. So the optimal solution to subproblem number 2 is this one. Z equals 41, x1 equals 4, and x2 equals 9 over 5, which is located here. Okay? So we are almost there. We have an integer value now, and we have a fractional value. Okay? So we are improving our solution, and this is what we just did. you can see how we're going to start branching our problem. So we start with subproblem number 1, and this is the LP relaxation, so this is the solution for the LP. Remember, both of them were fractional values. Now, we added constraint x1 greater or equal to 4, and x1 less than or equal to 3, and we found the solution for subproblem number 2, which is here. So the solution is x1 equals 4, x2 equals 9 over 5. We haven't touched this area yet. We're looking at this area first. Any questions so far? Okay. So the optimal solution to subproblem 2 did not yield all integer solutions, so we choose to use subproblem 2 to create 2 new subproblems. So we're gonna, you see that you still have a fractional value here, so you can repeat the process, add 2 constraints here, and have 2 additional branches. So choose the variable that is fractional in the optimal solution to subproblem 2 and branch. So the only fractional value is 9 over 5. 9 over 5 here. So we branch. We're gonna repeat the process, partition the feasible region for subproblem number 2 into those points having x2 greater or equal to 2, x2 greater or equal to 1. So these are your new subproblems which are coming from subproblem number 2. And here we are. When you add x greater or x2 greater or equal to 2, this is that line. That line is over the feasible region. So it's not touching this area. So any solution that is greater or equal to 2 will be infeasible. So this goes this way. So any solution above the feasible region is infeasible. And then you have this second constraint that goes down. And that defines subproblem 4 will be here, and subproblem 5 will be in here, this small area within or inside the triangle.
So you're talking just about the feasible region.
The feasible region for the new partition for subproblem 2. Yes. So we are adding these 2 constraints, x2 greater or equal to 2, and x1 greater or equal to 1, because we know this is a fractional value. So we are repeating this process. This is 2 point something or 1 point something. So 1 point, let's say 1.3. So this is 1 and this is 2, and you are adding those constraints again, which are the ones represented here. This case, they are horizontal, so they go up and down. So your feasible region now is here for subproblem 5. And the other feasible, but it's not feasible, the other area is this area, but you see that it's outside the original subproblem, which tells you that there will be no solution here. Now we're going to focus on this subproblem in this small area. Okay, so we have 3 subproblems that haven't been completed, subproblem 3, 4, and 5. So looking at this particular area now, which is subproblem 5. Subproblem 4 again is infeasible. So we can put that here. When you add this constraint, this is infeasible. Now we can focus on subproblem 5. Oh, something else. So the problem is infeasible, so you can basically delete that box saying that there will be no more branching in this area. because you're guaranteed to not find an optimal solution. So let's call phantom the branch. The set of unsolved problems consists of subproblem 3 and 4. So going back to this area, we're solving subproblem number 5 now. So if you solve that, you will get this solution. So now x2 equals 1, but you still have a fractional value here. So you can branch one more time in that subproblem. So let me show you that. We choose x1 equals 40 over 9. So we can add these two constraints to that small area. And when you do that, you're creating another subproblem or two new subproblems that are coming from this small new area. And now when you add those constraints, this is what happens. Now your feasible region, you're adding these two constraints. One goes this way, one goes this way. So the feasible region for subproblem number 7 is this line. Is this line. That's subproblem number 7. And subproblem number 6, the feasible region is just that point. You see why, right? Originally you have all this area. Now you're adding an additional constraint, so the only feasible region is this line. You're adding this constraint, the only feasible region is this point. So if you were to solve one of these subproblems, for subproblem number 7, the optimal solution will be in this point. And you see, now you got an optimal solution with two variables that are integer. So you found one solution. So when you go back here to this 3, you can add that in your 3, and this will be your first candidate solution, in which you have x1 equals 4, x2 equals 1, and the optimal solution is 37. But what happened? You still have two subproblems that you haven't solved, subproblem 6 and subproblem 3. So, candidate solution, solution obtained in which all variables are integer, lower bound for the original IC. So we still have two subproblems that we need to finish. So let's look at subproblem 6. Since this is the only point you have, this is going to be your optimal solution. So you got another integer values for your decision variables. So you can add that to your 3 now. So problem 6 with your objective function equals 40. And what happened here? Is this a better solution than this one? It is. You're getting a better optimal solution. You're trying to maximize. So that means that this becomes your best option. So you can delete this one. And we still have this subproblem to solve. So that is this area. So initially we focus on this partition, right? Now we are going back to this area. That's subproblem number 3. And when you search for the optimal for this area, you'll find that the optimal solution is 39, which x1 equals 3 and x2 equals 3, which is this point here. And guess what? That is an optimal solution that is integer. So you don't have to do anything more with this area. You can put that here. And now you're going to compare these two solutions. Which one is the best?
The big one. first try.
Your first try, you gotta, yeah, that can happen. Okay? So, and I did it on purpose because I knew that would happen. So that's why I started from this side. But still, even though you found an optimal that is integer, your solution is not better than the one you found. So you end up discarding that solution, and your optimal solution is this one. So the optimal solution is to manufacture 5 tables and 0 share with a profit of $40. And that concludes our lecture on integer programming. And now this is a lot too vast. We're going to go over this on Thursday again. So I'm going to go over the solution method for this problem. And I also have another example that I would like you to work on and discuss in order to finish this lecture. So that will be next Thursday, because Tuesday again we have the guest speaker.
Are you leaving Tuesday or are you leaving Monday? Will you be in the office Monday? Or you don't have office?
But you can always send me an email. Actually, I'm leaving on Sunday, coming back on Tuesday.
Oh.
So, but I'm coming back in the afternoon, so I will not be able to see on Tuesday. But if you need to see me, I'll be here tomorrow, or you can send me an email. Okay? Any other questions? Okay, so again, keep in mind that you have that opportunity to go to UC Berkeley. Even though you're not considering graduate school, you can go there. Maybe you would like it. And maybe you would enjoy the university. And
Is it from 8 to time?
no, it's within that time period. It's gonna be, there are gonna be more students. Yeah.
Let's stay finals.
May 8? Oh, okay. So that will.
Well, a lot of people don't have finals.
Yeah. Just take a look. I mean, even if that is a problem, you can always talk to the professor. Yeah. So it's paid, and it's a good opportunity, even though I mean, yeah, it's paid, so you don't have to pay. So you don't have to pay for it, and they're looking for students for their graduate program. So you never know. Okay, so let me know if you are interested. I'll post this on track.